All right, then. So now let's go through question number two. So question number two, it reads as follows. They say to us, a stat tank reactor has an internal cooling coil to remove heat liberated in the reaction. So I want to draw down this statement that we see over here. Um, so we have a stat tank reactor, right? So now this will be our stat tank reactor. And then inside of this stat tank reactor, we have a solution. And then here's our stir, the motor that stirs the reaction inside of the tank. And therefore, a stat tank reactor has an internal cooling coil to remove heat. So now let's talk about that internal coil they are actually talking about. So the internal coil is going to be given by, this will be our internal coil, right? We have our internal coil. So it has an internal coil, cooling coil to remove heat liberated in the reaction. So what's happening over here is inside of this, we're going to have heat, right? So this heat will be removed from the tank into the coil. This is where we are going to talk about the heat transfer, right? That's the only way to remove heat with this coil. So um, now that's what is happening over here. Just draw up out this statement over here. And now they say to us a proportional controller is used to regulate coolant flow rate so so as to keep the reactor temperature essentially constant. So now having a look at this statement over here, this is what we actually want to do. This is our objective, right? Our objective is to use a proportional controller. Remember, this is a control system of which we want to control the temperature constant. So meaning we want to get the desired temperature using a proportional controller system. So what's happening over here is to control that temperature that leaves the tank, to control the temperature of this tank over here using this coolant. This coolant, like I said, how is this coolant going to be in use to control this temperature at a set point as P? So we're gonna have a cold water, I'll write W1. We have a cold water that flows inside of the coil. And when this cold water gets inside of the coil into the stat tank reactor, what's going to happen is because this is cold water inside of the hot solution or a liquid, therefore, a temperature in terms of energy, it will move into the heat will be transferred into the coil because of temperature gradient. We know that the temperature will always move from high concentrated to a low concentrated of temperature where you have a less temperatures. Remember, this is heat transfer. Therefore, the heat will be then transferred into this, and therefore the water that's gonna leave outside on this side of the coil, it will be a little bit warmer compared to W1. So now we have the rate of W2 that's gonna leave this, which is a little bit warmer compared to that one because there was a heat exchange between the cold water and the hot solution, right? So how are we going to control this? We use the valve over there. So here we're going to have a valve that actually the flow rate of this cold water will regulate the temperature that remains inside of the stat tank reactor. So we're going to control the flow rate of the cold water, okay? So that's just how it works. So this is an objective. We need to determine the desired temperature, the set point, right? This is the set point of the temperature that we want to achieve. Now, they say to us, the controller has been designed so that the controlled reactor exhibits a typical underdamped second-order temperature response characteristics when it is distributed either by the feed flow rate or by the coolant temperature changes, just like how I've explained over here. This statement over here on how we're going to regulate the temperature and so forth, it's just explained over here. But now let's go back to this statement once more again to see the important terms like over-damped second order temperature response characteristics. Now, when we talk about the over-damped system, this is where we're going to talk about the damping factor or the zeta, right? So the damping factor, okay, this is S, it's not, I'm struggling okay. The damping factor, when they say our system is over damped, so that means the damping factor is going to be between 1 and 0, okay? The damping factor is going to be between 1 and 0. And most of the times, when the damping factor is between 1 and 0, this is where we're going to have the overshoots. It does not matter whether the overshoot it is 1 or the overshoot it is in sinusoidal. It really does not matter. But the overshoot always exists when our damping factor it is within a range of 1 and 0. Okay? And then also we are talking about the second order equation. So when you talk about the second order equation, we are looking at the transfer function. So the transfer function given by second order equation, unlike the first order equation, first order reaction, we know that here we're gonna have GS, which will be for second order. We're gonna have our gain over there, divided by our tau squared, S squared plus 2 pi tau S. Oh, I'm leaving the damping factor. So here we're going to have our damping factor. So we have our a damping factor multiplied by S plus 1, right? So this, it is the equation. Oh, I don't know why am I writing pi here. Why do I like pi? And now here we need only two variables. Let me rewrite that. It's my pen, my eraser. What do I have there? Let me rewrite that to fix that error that I made there. So meaning we're gonna have 2 tau, the damping factor, the damping factor multiplied by what? By S plus 1. Just always remember that you have two unknowns here. That's how I normally remember this one. Ne? So this is the transfer function for a second order temperature response. And then here at the top, we are looking at the gain. So if you do remember that the gain, it is actually defined by the change in the output divided by the change in the input into our system. So we'll look at the whole idea, what is, but in simple, we can even just look from the diagram. Our input, it will be the flow rate, and then our output is going to be our temperature, which is our set point, our process variable. So in this case, output divide by the ratio of output and input, it is given by the gain, which is denoted by letter K. And then here we have our characteristic expression over here at the bottom for our second order system. This will be our characteristic equation. So our characteristic equation to determine all of these variables such as T, tau constant, tau, which is the time constant, the dampening factor, to determine these values, numerical values over here. This is when we're going to use the different equations, such as the equation for overshoot, the time peak. We're going to use the equation for the period as well, but we will see when we get to those kind of questions. So that's what is basically happening based off the scenario that is provided over here. They did not give us the equation, they did not give us the diagram. So to make sense out of the statement, it's better to draw it down so that we can understand what is basically taking place. So now let us start with the first question then. So now to answer question number 8, says to us, the feed flow rate to the reactor changes suddenly from 0.4 to 0.5. If you do remember, the flow rate, the feed flow rate to the reactor changes suddenly from zero point 0.4 to 0.5 kg meters per second. So we are changing the input. If you still do remember, the flow rate, it is our input. And the temperature of the reactor contents initially at 100 degrees Celsius changes eventually to 102 degrees Celsius. So now here again, we are talking about the change in temperature that is leaving, right? So that will be our output. Now the question is, what is the gain of the transfer function and the feedback control that relays changes? So far, like I said, here we have a transfer function, and this is the gain of the transfer function. And how to calculate the gain aside output, change in output over change in the input. So to calculate our gain without using this big giant equation, because we don't have time constant, we don't know, we just don't have these variables. So the simplest way and the easiest way is to use the equation that says the gain is going to be change in the output of the system divided by change in the input of the system. And we have already defined that our output is going to be the temperature. So our final minus initial. So our final is going to be 102 degrees Celsius. So here we have 102. Subtract our initial, which will be 100 degrees Celsius. So I'm just writing my units there outside because they say to us, be sure to specify the units, obvious to the final answer, by the way. And therefore, what will be the change in the input? We are looking at the flow rate in kg per second. So this will be the final flow rate. This will be the initial flow rate. So we are looking at 0.5 subtract 0.4 kg per second. And then 102 minus 100. Where's my calculator? There it is. So meaning we're going to say 2 divide by 0, 0.1, we get 20. So that means here we're going to have 20 degrees Celsius second, because the second will go at the top, per kilogram. Therefore, this is how we calculate our K. We are done with question number 8. Simple as that. And then now we're going to move to question number B, where it says the operator notes that the resulting response is slightly oscillatory with maximum estimated to be 102.5 and 102.0 degrees Celsius, occurring at times 3060 seconds after the change is initiated. What is the complete process transfer function? Right. So now here, what's happening is apparently there is an oscillator with maximum. So the oscillator that they are talking about over here, it is due to our output. Our output, it is the temperature. If you still do remember, our temperature initially started at 100 degrees Celsius, and then it moved to 102 degrees Celsius. Apparently, from there, then it will oscillate between 102.5 and 102, meaning it will shoot up again from 102 to 102.5, and therefore there will be an oscillation throughout until we get our set point once more again. So to make sense out of this diagram, to make sense out of this statement, right? Like I say, this is all the statements, and it's better when we draw so that we can see what is happening. So this side we have the temperature, and then this side we have the time. So I want to write down this this response curve that they are actually talking about over here. So our temperature, assume that here it's 100 degrees Celsius, will change from initial temperature to 102 to 102.5. I'll draw a nice curve that can help me to explain this. Or let me just shoot it up. Gosh, what happened now here, this side? I'm struggling to draw. I'm not good with this, but let me try it once for the last time. See. If I fail, I will leave it as it is. Right? Until we get that response to overset to the set point. So now what's happening over here is this temperature at this peak, at this first peak, it will be 102.5. And then at the second peak, our temperature will be 102, right? And therefore, this will be, which is our set point over there. Now, this is what is happening. The reason why we draw this, I'm drawing this thing here. The operator notes that the resulting response, this is the response, right? Is slightly oscillatory. This is oscillation with maximum estimate to be 102, 102.5, and then it goes back again to 102. It goes back to less than 102. It goes back to less than this peak over here until it goes back to the set point again. Okay, occurring at this time. So the first maximum peak will occur at this time over here, which is most definitely our time, which will be 1000 seconds. And then the second peak, which is in 102.0, will occur in 3060. After the change is initiated, what is the complete process transfer function? So basically, we are looking for a transfer function for this response that we see over here, right? Um, to determine the transfer function for this, how are we going about for this one? So we are looking for something like this. K already we have it. So we need T, we need the tau, and we also need the dampening factor. These are the two variables that we just need so that we can substitute them over here, and then we get our transfer function. But the question is, how are we going to get these two guys over there? So like I said, there are equations that are associated with these variables that we want to talk about. Now, we have the equation for overshoot because looking at this response, have the overshoot because again, like I explained, this is the underdamped system. So when you have the underdamped system, so that means you're gonna have the overshoot. It is expected. So the equation for overshoot, I'm gonna explain that so that you can understand why we need the equation for overshoot. So the equation for overshoot in this case, it will be given by e to the power of negative pi multiplied by dampening factor divide by root of 1 subtract the dampening factor squared, right? So this is the equation that we use to calculate the overshoot. So the overshoot, let's talk about the overshoot, which is from here to there and from there to there. This is an overshoot, right? It is not expected because we want to maintain the what? We want to maintain the set point. So this is most definitely an overshoot. So at this point in time, it has overshot by this part over here, which is 102 to 102.5. The difference will be 0.5. And then again, the overshot here, it's going to be 100 to 102, whereby the difference here is going to be, it's going to be 2. Yeah, it's going to be 2, right? So another way to calculate the overshoot, we're going to say the overshoot is the ratio of how the sinusoid or the oscillation overshot. So from the slides, if you still do remember, we have A over B over there. So in this case, we're going to say our overshoot is equals to 0.5 divided by 2, which is the difference that we have just calculated over there. And then the reason why I'm calculating the overshoot aside without using this equation is because I want to use this equation to determine the dampening factor. Remember, this is my objective of me writing this equation to start with, because I want to determine the over damping factor or the zeta. So in this case, I cannot have two unknowns in one equation while I'm looking for another unknown. So hence I'm calculating the overshoot. So in this case, our overshoot, we have 0.5 divided by 2, and then our overshoot will most definitely be 0.25. And then when we approximate this overshoot in percentages, we have 25%. Now I'm going to substitute my overshoot there, which is 0.25, which will be equals to the exponent to the power of negative pi. What's this thing? The dampening factor divided by 1 subtract the dampening factor squared. Then introduce ln on both sides. So here I'm going to have ln of 0.25 is equals to, here I'm going to have negative pi, the dampening factor, divided by 1 minus this to the power of 2. And then now we can see that out of this equation, we have now one unknown. So to solve for this unknown over here, when you perform your mathematical concept, just cross multiply. But before you cross multiply, you can introduce your root sign on both sides of the equation. And okay, let me take you through the steps. So this multiply by this, we are most definitely going to have what? We're gonna have ln 0.25 multiply by root of 1 subtract the dampening factor is equals to negative root negative pi this right. So now let us get rid of the square root. We introduce square root sign, we introduce squared on both sides. So here we're going to have ln of 0.25 squared multiplied by 1 subtract the dampening factor squared is equals to, here we're going to have pi squared, we're going to have ln dampening factor squared. Then let's distribute here. We're going to have ln of 0.25 squared minus ln of 0.25. This squared is equals to, here we have pi squared, the dampening factor squared. Then I'm going to group the dampening factors together. I'm going to have negative ln of 0, oh, let's not forget squared there. 0.25 squared, the dampening factor squared, and then here I have negative pi squared, the dampening factor squared, and then I transpose this one that side, it's going to be negative ln of 0.25 squared. Hopefully we are not making any errors. So let me take it here. So we're going to have negative ln 0.25 squared minus pi squared. Then here we have the dampening factor squared, which will be equals to negative ln 0.25 squared. Then here we're going to have the dampening factor squared. I'm struggling to draw the constant. So we have fraction negative ln of 0.25 squared divided by negative ln 0.25 squared. Let me see, minus shift pi squared. I get 0.1629 blah blah blah. But because I'm not looking for this, I'm looking for not looking for this squared, dampening factor squared. I'm gonna have to get rid of that for using outside. And therefore, my dampening factor will be, God, struggle to draw the sign. Introduce root sign on both sides, and then I get 0.404, but to two decimal place will be 0.40. Now we are happy that we managed to get our dampening factor. So What is left is to determine the time constant. So to determine the time constant, now we're going to use the equation that says period is equals to 2 pi tau divide by 1 subtract dampening factor squared. Okay, this that has exponential, we use it for overshoot. And this that has the tau and the dampening factor, we use this one. So the question is here, we are looking for tau. So we do not have a period for now. We have another variable here, which is dampening factor. Already we know it's 0.4. But the question is, how are we going to calculate P? Now, this is how we're going to calculate P. Remember, overshoot, we use the graph. P, still going to use the graph. It's a period. So when you talk about the period, we look at the points that are in phase. Okay, the points that are doing the same thing at the same time. We say those points are in phase. Or you can simply say you look at the complete wavelength. This is a complete wavelength from this point to that point. So we are talking about the period of a wavelength, which is going to be here. This is the wavelength, which has a period. Can also talk about the frequency of that wavelength. So now the period, here we're going to use these times over here. We're going to look at the difference of the time between 3060 and 1000. So to calculate the period, we're going to say 3060 minus 1000, and then we will get 2060 seconds. That will be our P, which is our period. Okay? Right. So now the question is, then if this is our period, how are we going to get the time constant? We substitute P over there. We have 2060, which will be equals to 2 pi. We are looking for tau divide by 1 subtract 0.4 squared. I'm gonna multiply everything by the reciprocal of this to get the tau, meaning I'm going to multiply 2060 by the reciprocal of this, which is this minus this divided by 2 pi, and then I will get my answer over there. Let's see how much is it. 2060 open bracket fraction root 1 minus 0.4 squared divided by 2 times pi. And then the answer is 300,49. So it will be 300 seconds. This will be our time constant. And therefore, remember, the aim was to calculate tau. The aim was to calculate damping factor. The aim was to get the gain so that we can have the transfer function. Reminding you once more again, the transfer function, it is given by this equation over here. K over tau squared plus, remember we have two variables over here. We're going to have 2 pi. I said 2. I love pi. I don't know why I always write pi here. 2 tau, and therefore the dampening factor multiplied by s plus 1. And therefore, now let us substitute. Remember, we said our gain, if you still remember, it was 20. We said our gain is 20. We got our gain there. So we substitute it over there, that our gain will be 20. And therefore, the tau is 300 to the power of 2s squared plus 2 multiplied by tau, we said is 300, multiplied by dampening factor, we said 0.4s plus 1. And therefore, this will be our final answer. G at S is equals to 20. This will be 90,000 S squared. And then we're going to say 2 multiplied by 300 multiplied by 0.4. We get 240 S plus 1. Therefore, this will be the transfer function. Okay, then I hope that was clear.